Hello, my name is Stephen Brennan, and I'm here to talk about my final project. And I'm doing it alone because I did the math, and if I redo the Connect Math stuff, get 100 on it, and I get 500 points on this, I can still get an A because it rounds to an A. So that's fine with me. Okay, let's get this PowerPoint started. All right, so we begin my final project, and I really like my theme here. It's a nice font. Okay, measurement of the density of the numbers and the law of large numbers. Oh, I guess I should move my cam. There we go. That should be out of the way for the most part. In the relativity of speed. Okay, I found some pictures, and this is probably the easiest way I can explain it. It's probably a little cringy, but these pictures are from, oh, whoops. Sorry about that. Very sensitive. These pictures are from a game set in space called Mass Effect. Cringy, but it's set in the Milky Way galaxy. For the most part, it's basically accurate. But it has these things. This is the Milky Way galaxy here. And of course, as we know, there's the galactic core in every galaxy, or most every galaxy. And all these clusters, or nebulas, as they're called, like this is a nebula down here. Every one of these circles represents a nebula. Of course, these aren't all the nebulas in the Milky Way galaxy. It's just the ones in this game. But these nebulas rotate around the galactic core, which that adds speed up onto itself. But then if we go into one of these cores, like one of these blue circles here, we get into this nebula or a cluster. And each one of these circles is a solar system with a sun. Well, I guess that's the definition of a solar system, because of course there's tons of dead planets everywhere, but that's beside the point. Each one of these are a solar system. And then, of course, if we go into that, then we have a map of, let's say, just our solar system, just for simplicity's sake. Then that is also our solar system is rotating with our home nebula here, and then that's also rotating with the Milky Way galaxy here, rotating around the galactic core. And then if you zoom out even more, then you have the whole universe, which is different, not different Milky Ways, different galaxies, just rotating. Well, the current theory is how galaxies move is the Big Bang, everything's still currently expanding outward, but gravity plays a big hole in that, with the Andromeda galaxy meeting to collide with the Milky Way galaxy in like 150 million years, and that's just slowly coming in. So back to the question, relativity of speed, it's what you want to judge what's coming, or what do you want to consider in your measurements. If it's something that has to be like everything we can quantify, and even stuff you need to estimate that we can't quantify, some something like that. But basically, it's just train of thought here. Basically, when you just look at it, we're going really fast. Measurement is relative to what you want to consider. If one is measuring your hand speed, you have to decide if you want to put the Earth's rotation into that equation. And then if you want to do that, do you want to put our solar system's rotation, our cluster's rotation, our or our let's see. Oh yeah, the Earth's orbit first of all, or the Earth's rotation, then the Earth's orbit, then the solar system, then the local group is actually a cluster of galaxies, then the Milky Way orbit, or then like what gravitational pulls affecting us with Andromeda galaxy. There's just so many, and then of course the local cluster with multiple galaxies in this general vicinity of space. That's just how scientists measure it. But it's just what we want to keep in mind if we're doing measurements for something. Relativity of speed. I mean, we're just going really fast. I remember a Bill Nye the Science Guy episode where this like farmer girl's just sitting on her porch just talking about how fast we're going, and she just keeps getting faster and faster and faster, and she's just getting more excited and more excited just the more she thinks about it, because it's just mind-boggling when you really look about it. And that's just everything with space, really. It just a lot of things out there, a lot of things to keep in mind. And then the relativity of size, kind of the same thing, but not really. The bigger a body is, the more gravity it has. Due to that simple fact, the faster it is. On a cosmological scale, everything's nearby. Like this nebula here. Okay, this small little nebula, there's probably thousands of these in a single galaxy. Well, then if we zoom out, okay, there's a galaxy there. Oh, wow, we can see a whole bunch of different galaxies. But then if we zoom out even more, we start to see clusters, or what scientists just say clusters. And it's basically just a group of galaxies. Forgot the word there. So on a cosmological scale, everything's nearby if you zoom out. If you zoom out hard enough, just like the misleading data in the future slide we're about to get to. If you zoom out, everything seems nearby, and like it's just a good way to mislead data. But I'll get into that later. But yeah, it's all about perspective. If you were to look at the observable universe with no scale in mind, one would think the universe is quite small, because the current view of the universe, the observable universe, if it's basically just a giant circle with a whole bunch of dots in it. So like if you zoom out far enough, you'll just think it's like a little ball or something. Of because of our limitations with what we understand at the moment, but that's the general gist of it. An asymptote. I think I'm saying that right. Okay. Well, for when we were talking about ibuprofen, an asymptote is a line that will never reach, not necessarily the x-axis, but it will never cross a certain threshold. But in this case, it is an x-axis. So like this line will continue indefinitely, never crossing the x-axis. It will never approach a given curve. It does not meet a finite distance. The curve will never touch the x-axis. The ibuprofen will always be in your body, according to this graph at least. The half-life varies from any kind of drug you want to consider. And my algebra 1 teacher described an asymptote, or she was describing something like an asymptote. I don't know if it's the same situation. Or I guess I'll talk about it in this slide because it applies more. And this is the number of times you can divide stuff in half. You can divide a number in half indefinitely or double it indefinitely. But as I was saying, what my algebra teacher used to say, she used to say, well, imagine you get a piece of paper and you cut it. Okay, cut it in half. Okay, cut it in half again. Okay, just keep cutting it in half until it's so small. Like, okay, well, it's hard to cut something in half. Okay, then get a cockroach and give him his little scissors. Then he can start cutting it in half. And just like how she said it, it was just little cockroach. It was just very funny, but a very clear way to understand that something can be divided or cut in half. Well, I guess cutting in half is still dividing that paper in half. but but yeah, it's just an indefinite amount of time you can divide a number. It just will get a lot of decimals mathematically, a lot of decimals and a lot of zeros, zero places at least. Okay, and theoretical and empirical probability. The empirical probability is an event given numbers of times an event can divide the total number of incidents observed. Basically, what it will always end up to be, which is basically the distribution curve in the case of this, where the theoretical probability on is the number of sorry, got a text. Where was I? The theoretical probability, on the other hand, is the number of ways a particular event can occur divided by the possible number of outcomes. So basically, flip a coin 50-50. At least it should be. Mathematically, it should be 50-50. Or in this case, because we had two dice, yeah, it'd still be 1 out of 6 chance to get all of these? No, that's not right. 1 in 12? No, because you can't get one. Would it be 1 out of 11? I don't remember. But yeah, you get the point. And the law of large numbers and the central limit theorem. It's basically well, I couldn't like find a finite difference between this and one of the empirical probability, because basically the law of large numbers is the principal probability. Given enough instances, the results will always end up looking the same, just like this distribution curve. If we eventually roll these two dice enough and record the results, like in this case it's 21,000, it's basically the same all around. It's just the probability. It's just what happens. What happens every time. And I'm trying to think what it would look like if you flipped a coin. I guess it'd be the same. It just the two bar graphs would be generally even, I guess. But this is just a distribution curve. I mean, it will eventually look the same. And of course, there's probably more instances with more than just two dice. Misleading and false data reports and assessing resources and information. So misleading graphs. Misleading graphs, I hinted upon them when I was talking about the universe stuff, relativity of size. Basically the same thing. If you zoom out far enough, just like the universe, everything seems quite small. Well, if you zoom, wait, is this out or in? Yeah, if you zoom out in a bar graph, like if I take this graph and just zoom out, then there hardly seems to be a difference. And this is the accurate portrayal of this data here. But then people, well, they're both, first of all, they're both accurate portrayals of the data. It's just this one is misleading generally, if for those who don't pay attention to the y-axis, I guess. But yeah, they're the same graphs. It's just this one is zoomed in so close, so you can just see that finite difference, and you can see the unemployment rate for Clinton was really high compared to Bush. But if we look at the x-axis, it's only like a tenth of a hundredth of a percent. Yeah, I think so. 100th of a percent, basically, or maybe 200th. Well, whatever. It's misleading. Misleading information is used to sell products, and at this point, just like political goals in mind, and it usually benefits just well, it's just to benefit whoever you want. You can make data look however you want, and if it benefits you, of course, they're going to do it. Oh, too far. And misleading graphs to mislead the viewers. I couldn't think of another way to really word this, so I just found another example of what we did in our Excel report. People should know how to read the data. This is the accurate portrayal of the data. Well, like I said, I keep saying that. They're both accurate portrayals of the data. Just this one is misleading you because it doesn't, the y-axis, yes, doesn't start with 0. So this one is just super zoomed in, so you can just see that little bit of difference. And of course, you can see that over here, but when you zoom in on it, it's just like more distinct. And people would think, wow, Emily is I think this was bowling. Yeah, bowlers. Emily was a really good boulder bowler, while these other two weren't that good compared to her. But in reality, I mean, they're both really good. And if we had another source, it'd probably be like down here. But that's besides the point. People can make data look however they want, and they'll do it if it benefits them. And the correlation between GMO crops and various diseases. I chose just these two graphs from the Excel report. And in this, we looked at the BT corn. I forgot what BT meant, but GMO corn planted, and it is represented by these blue lines here on both these graphs. Of course, you can see it's the same data, but then the different disease is arthritis and bowel disease, and you can see one could put two and two together. Well, obviously, as this graph has done, um, and you can see a correlation between the two. Like they just seem to rise along with each other. Like as corn rises, or corn, as the acres of corn is planted, it just seems that the general population gets these diseases more and more. But of course, I like to keep in mind, just because there seems to be a correlation doesn't mean there is a correlation. Not saying that this is totally 100% wrong. Yeah, I'm just saying that there's 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 thousands of different variables to consider when you're talking about stuff like this, because like what we eat in correlation with diseases, it's it's there's just too many things to consider. You can't just say it's one finite thing. And yes, that could be a contributing factor, but that can't be the only thing for the most part. And FDA, data reported by the FDA, they encourage this ideology because the FDA acknowledges looking at one thing and seeing correlation does not mean they're connected. There are other reports full-heartedly agree that is undoubtedly connected. Also, there's no such thing as a non-genetically modified food. Everything we eat is, well, plants, everything we eat is genetically modified to an extent. Even corn. We modified corn in the ancient eras of our of humanity, because I believe corn used to be like this big, and I think same with horses. Actually, horses used to be like maybe Great Dane size, and like we just bred them to be bigger. Like we've been doing it since the dawn of time. But yes, the FDA acknowledges that there is no correlation between GMOs and these diseases that we looked at, which was bowel disease, arthritis. Number of deaths, I think, was one. I don't remember the other. There was like three others I don't remember. And the probability of guessing on a multiple choice test. In this one, we looked at the formula of binomial probability in Excel, and we looked at different formulas actually, but of course, we would want to use the Excel one that does it for us. But basically, we looked at, I think you said it, it's probably in your PDF, but you said um, this guy comes to his friend and says, hey, let's go to a party, and let's just party tonight. It was like, oh man, I have to study. I have to study for this 10-question test. And like he said, nah, it's fine. I guessed on that test and I got 8 questions right. I was like, oh, okay, sure, that sounds like a good deal then. But then if we actually do the math and take everything into consideration, mathematically, it's not a good probability that you will score 8 by just guessing. Because as we resulted, all these formulas result in the same thing. As we found out that it's only 0.039% chance that you will guess 8 correctly out of 10. And how we quantified that was the probability of getting it right, which multiple choice we assume out of 4, and the probability of getting it wrong, which is 3 out of 4, naturally, respectfully. And we just plug and chug all these formulas that you didn't make them up, but you found them. We copied them from you, and we just found that, of course, all these formulas do the same thing. It's just that they're written differently. And this one was a pain right here. You remember you had to help me with that one. Too many um, parentheses. Yeah, parentheses. I wanted to say quotation marks. But of course, naturally, we'd want to use the Excel version that does it for us. And it's even labeled nice and neat for us to do it. But basically, the probability of guessing on a multiple choice test, not so good. Mathematically, not so good. You probably don't want to do that. Skip on that party, buddy. This was a fun one. Expected outcome of buying a lottery ticket. People are always optimistic of these tickets until they see the odds, if they ever see the odds, which is an important factor. From a regular person looking at the odds, not looking at the odds, it gives them hope, I would imagine. Of course, if it doesn't give them hope, why would they buy it? And from this point of view of having the odds, the lottery is a sham, obviously. How it, it's just it's just a sham. And from a seller's point of view, like selling the tickets, they're making bank, or like the people who produce the tickets, not like the gas stations. Well, the gas station too, I imagine a little bit, but they're making bank. And of course, and they not skew, that's the wrong word. They mess with the probability of winning, so it's not like a linear thing. It's just not random, but it's strategically chosen so people win enough so they feel like they're winning. So like let's see here, like this one is one out of 140 to win 15 bucks. Like that's a big chance. But then if you look at 20, oh, it's only 1 out of 48. Okay, that's not so bad. But then the next one, they get you. It's strategically putting those probabilities in so you keep on losing, but you still gain that hope for the occasional chance that you do win. That 1 out of 14, that 1 out of 8, right here. So, and when people buy these without looking at the odds, they think, "Oh, surely I can win something." But then when you look at the actual odds, then I I don't know why you would buy it, frankly. um, honestly, one out of 3,400 to win $200. It's not really a good chance for me. Plus, it's just glorified gambling. Who cares? Just don't buy lottery tickets. Oh wait, just to make sure I'm not skipping slides because it's very sensitive. In the probability of being obese and obese, bleh. The probability of being an obese American and being an obese American with type 2 diabetes and high blood pressure. We made a Venn diagram on this in our Excel. Basically, the percentage of Americans with type 2 diabetes, high blood pressure, obesity, and we used a Venn diagram naturally because that would clearly answer this question. And the probability of being an obese American is 3.1%. Wait, that doesn't sound right. Huh, that's weird. I don't remember why this says that. I guess it was another thing, and I just didn't look at the Venn diagram close enough. But if we look at this table, this is the correct data. The number of percentages, the percent of Americans that are obese are 29%. Um, that's why I was confused when I saw that. I'm like, no, that can't be true. But then we have percent of Americans in the Venn diagram, so I forgot what that number means. But if we look over here, it's 29% of Americans. Oh, yeah, yeah, I remember now. Yeah, this is the percentage. Yeah, okay, I remember now. Um, so it's 29% of Americans, and Americans with type 2 diabetes. Where is that? Oh, right there. Just type 2 diabetes at first is 90%. So if you're obese, like 90% chance that you have type 2 diabetes. And same thing with high blood pressure, a little less than chance, which is well, never mind, is a 86% chance. So it's uh, it's pretty high. And of course, all these things like correlate with each other. Like it's a domino effect if you're well, it's a domino effect if you're obese, I guess I should say, because that's why the percentages are so high. Like out of these 29% of all Americans, 90% of those are diabetic, type 2 diabetic, and 86 is has high blood pressure. So like one can assume, and I've always assumed, if you're obese, then yeah, you have a higher probability of gaining diseases. Well, disease is the appropriate word. I guess not. That doesn't sound right, but it's just the higher chance you would get something like type 2 diabetes or high blood pressure because they correlate with each other. Like if you're obese, it's a domino effect that you'll probably end up getting one of these eventually. And the probability of being obese, depending on the population on where you live in the US, I went back to that website that you took us to, um, in whatever scenario Excel report it was, and I used the snippet tool and I selected Arkansas because, of course, we live there. And the probability of being obese in Arkansas is 35%. That's pretty high. And according to this website, we are the seventh most obese state in the U.S. Which 1, 2, 3, 4, 5, 6, 7. Hey, at least we're on the bottom of the purple scale. We're at the very bottom according to this, so that's a plus, I guess. But we can see that usually the South is more obese, and of course Florida is an anomaly when it comes to the South, in my opinion. It's not really like the rest. At least the more southern you go in Florida, northern Florida is probably very stereotypical southern. And yeah, we can see here on the West Coast, I almost said East Coast. The West Coast is America's standards generally healthy. And the healthiest state is Colorado, which and Hawaii. Hawaii, really? I find that a little obscure. That's weird. Because, well, not to be mean or anything, but like, it's very rare that I see a Hawaiian that isn't like just really fat. But I guess that's beside the point. Well, Colorado and Hawaii are the lowest states like that. And then like places like Alaska, that actually makes sense because you have to survive the winter there, and people actually put on pounds to survive the winter. Everywhere else though doesn't really have an excuse. And but you can see how there's just these giant clusters of people of obesity rates in the U.S. Mm. And sadly will probably go up for quite a few years at least. Oh, I forgot I was on a new topic, and I forgot to say the slide titles for all these. This is the third one in this one. The probability of an event given a population and a sample. Impaired driving. Well, and that's the topic for these two. Just to fix that mistake. Impaired driving in the U.S. and the probability of being on a rural, rural road versus being in the city. And basically, the only data that we collected on this was this graph here was urban and rural. Rural. God, I can't say that word. Basically, dirt roads. They're generally okay. It's not the 50s, Stephen. Come on, they're not dirt roads, but they're usually unkempt roads, to say the least. Um, but yeah, it makes sense that accidents happen more often, and I don't know why I put that on there. It doesn't really match up with this data, but whatever. This data does. Excuse me. But it generally makes sense why. Sorry, a little burpy. Rural roads would be more accident prone because I guess like late night driving, I heavily assume that there's like less lights, less traffic lights, more stop signs and the such. It just makes sense. And of course, in the city, it's well lit. Of course, accidents happen in cities, urban areas, but but they have lights, they have clear, generally clean roads, traffic lights. They have all that good stuff, and it just makes sense that rural roads would be. I keep wanting to say dirtier, more accident prone. In the polydrugging in the British Columbia in the U.S. population, the British Columbia data probabilities may or may not be represented. Well, this is the data that we gathered in report 2, I believe. Just this massive Venn diagram that we copied from, or not copied, we made it ourselves, just used that as a reference point to make this Venn diagram from the British Columbia. And this was does it say in here? I'm pretty sure this was car accidents, what was in the recipient's a bloodstream, bloodstream when that accident occurred. And as we can see, 20% was alcohol, same with medication, and 10% other random drugs, which I assume just illegal drugs that they don't have a medication for, I'm guessing, and about 7% of cannabis, which I found that surprising. Well, for Britain, I guess I should say. Wait, British Columbia. That's never mind. Never mind. I'm stupid. Never mind. But basically, all these categories would apply to the U.S. because I imagine in like every single car accident, there's a high chance that one of these would be in their system, especially medication. Heck, I don't have the stats on it, but I imagine most, like, I want to say like 95% of adults in all of America usually has medication, if not like 99%. I think it's like very rare that people don't have medication in America at least. so, so yeah, all categories would apply. And the probability of approving ratings of the president, depending on what party um, the American belongs. So, of course, everybody has bias, and it's a real concern when trying to make a sample. But in this case, I think this was just two general states, like a Republican state and a Democratic state. Of course, two clear biases. Um, and the sample was the state itself. I forgot what states they were, but this was a Republican state. Of course, they approved very highly, but a decent percentage also disapproved. And then over here, a Democratic state, oh, surprise, surprise, most of them disapprove. And I'm also surprised at this percentage that does approve. I'm surprised at both the disapprove and approve ratings on the lesser known margins in this pie chart. So yeah, just when sampling, you need to worry about the bias. But of course, I think this was just to prove a point, and they chose in this specific data we chose a state that had a bias towards a political party. And the probability of being a man or a woman and a man in different branches of the U.S. military, honestly, more women than I thought, to be honest. These are basically just the same graphs, just portrayed differently, but these ones have the exact numbers on it, and it's 3D and cool. Well, I guess that's 3D, but this is clear, so it's cooler. Um, the blue is the women, and the orange is the men, and I guess women are they're pretty evenly close to men in Navy and Air Force, which that's surprising being in the Navy. I just never would have thought of that, to be honest. Like Army and Air Force, I've heard of women in in there. And of course, I know there's women in all branches, but I'm just surprised how much we're in the Navy. So yeah, as you can see, men generally outnumber women, but their numbers are rising. They are getting up there, which is good in my opinion, I guess. So the probability of like a Marine, if I chose 10 people, let's say, there's like a 1 in 10 chance that you'd be a woman, or well, I guess that would round, so 2 out of 10 chance of being a woman, and this would be a 4 out of 10 chance of being a woman, or 6 out of 10 chance of being a man, of course, and yeah, that's the probability of gender diversity in the military. Differences in standard deviation given two population and samples analyzed height of Army recruits. Oh man, and the height of mall shoppers. The heights of and we have two different data points here. Oh, I'm sorry, I'm not feeling too good today. We have two different pieces of data here: the heights of the Army recruits by inches, and the heights of random, just completely random mall shoppers in inches. They're both in inches. And as we can see over here with this, we record the heights in every recruit. I guess it was out of 9. Yeah, this one was out of 9 too. 9 people in both situations, and we recorded their height. Okay. The military seems pretty consistent, which makes sense. Weird analogy, but I guess if we took like basketball players, everybody would be super high. So it'd basically be the same situation. So the trend line, because the standard deviation or the average or whatever is dead even, because it's basically pretty linear on, because there's only slight height differences between everybody in the military, because basically everybody's adults, but in this case there are like obvious cases of little people or kids. And of course there are the oddball that are the oddball that doesn't sound right. There are the few rare cases where people are generally high in height. Rephrase that. But in this one, the trend line is pretty, like, it is just super close to all the data, because the data itself is pretty close. And in this one, the trend line is it's basically you can see it's in the middle of all these dots, but the dots are still like heavily above. So like how I like to think of it, this trend line is like the average. Well, I guess it is the average. It's the average of all these like different dots going up, and it's the average of all that. Which of course this actually looks like it's kind of going down in the Army one here. But that's just because there's just a lot more cases of little lower height in some of the recruits. But of course, this is taken from a controlled sample, people who group together that are generally, well, in this case, generally the same height. Like I said in the basketball situation, if you took everybody from basketball, everybody would generally be the same height. And random shoppers, it's all over the place. So what I'm getting at, random, depending on like the kind of sample size you're getting or what kind of data you're trying to collect, you want to make sure your sample is appropriate for that. And how do scatter plots trend? I forgot a comma. Trend lines, or no, I guess that is a word. One word. How do scatter plot trend lines, width of a box and whisker plots? That's a comma I didn't mean to put in. Correlate with the size of standard deviation. Um, well, for this one, I used the same graphs. If we go back, the standard deviation of the Army recruits is 4, And we can see it's 4. It's pretty tight knit with all the other data. And if we go to this one, the standard deviation is 14, which is more sporadic, which that's why, and that's taken from like the average of all these things. So that's why the trend line is in the middle, but there's still points everywhere. So it's a higher number. And these linear trend lines, well, I'm pretty no, there are exponential trend lines, like in the half-lives. Um, just the trend line was really close. And these linear trend lines, the estimate is a statistical technique to aid and interpret data. So, like, just we can see the general idea of this data. Like I said, I just consider this kind of like the average, but the average takes form. So it's just easy for us to infer the data. And the probability of belonging to each age group and using distraction devices, cell phones. Um, oh, that's funny. The brightness on my face cam is just way darker because of all the black in the screen. But whatever. The probability of belonging to each age group and using distracting devices while driving. Well, as we can see over here, I need to remember to point with the mouse, not the finger. With the age group of 16 and 24, there seems to be um, a lot more. Wait, probability of belonging to each age group. There seems to be a lot more cases of people using the distracting devices um, while driving, and of course, it kind of evens out with the next age group, 25 and 69, and I don't remember if this was deaths or just people using distracting devices. Let me. Well, I'm pretty sure it was the amount of deaths in each age group using distractive devices. So so as we can see, over the years, it seems that this age group is going down, but it did start quite high. But over here, this is a slower descent of using distracting devices. I'm just going to say phones. I know there's more than just phones, but I'm just going to say phones for simplicity's sake. And then 70-year-olds, it surprised me that even 1% of them actually use distracted devices while driving, because that's 70 plus. That's a dangerous thought, to say the least. So let's say my age group is over here. I'm 20. The probability of me driving with a distracted device, if I drove, haha, cheated the system. Um, the probability of me using a distracted devices if I did drive would be, I guess, remarkably higher than all the other age groups. It'd be, at least in this first year, it was like 8.8%, which I'm surprised it's that low. I don't remember where we recorded this data, but I feel like it should be higher. And how do the scatter plot trend lines, width of box and whisker plots, and width of bell-shaped curves correlate to the size of standard deviation and the coefficient of variation? So basically, I just took the same data here, and I just added the standard deviation. So this one we can see is the standard deviation is 1.5%. Wait, is the standard deviation supposed to be in percent? I don't. I don't think it is, but okay. Well, just ignore the percent if it's not. I'm pretty sure it's not. The 1.5 standard deviation, you can see there's a remarkable decrease, and then in the next one, we can see 0.9% is this, or zero point 0.9. The standard deviation is 0.9, and then we can start to see that steep hill, that steep decline, or let's just say just that steep decline there is getting a more reverted. So we can assume if we see a standard deviation of zero point 0.3, we can assume it's more level compared to all these others, just using this data we can assume. And it is. It's zero point 0.3. The standard deviation is zero point 0.3 on the 60 age group. And we can see that the trend line is a lot more level. And then with all this information, we can assume if the standard deviation is 0, then it's just a 100% linear, just flat horizontal line on this graph. And we can assume the same thing with the width of the box and whisker plots. I didn't put any on here, but I think, yeah, we can just use these box and whisker plots. The standard deviation for this guy was super small, so this was also super small. But this one was very wide. Did I? Oh yeah, the standard deviation for this one is 14, so we can see that this is it's more stretched out, just like the trend line itself. It's going up. It's more sporadic, where this is just linear. This box and whisker plot is a lot more narrow and precise, where this one is a lot more, well, it seems just a wide ratio due to the fact of the random sampling. And the probability of belonging to the percent of the population with healthy body mass index scores. Well, we can assume that it's, well, no, we can assume. We know it is, there's a 68.2% chance that you would be considered healthy because of the blue section in this distribution curve. Well, I guess healthy would be this, like, the perfect healthy would be right in between this, but I'm pretty sure these were considered healthy, both these sections. It just one was lacking. One was a little lacking on nutrition, one was a little overcompensating, just a little bit, but they were still considered healthy. So if we just add those up, it's 68.2% chance that you'd be healthy, at least looking at this distribution curve. And this is vitamin D consumption, but I just grabbed a bell-shaped curve with the markers on it. And of course, these graphs aren't really in the right place, but whatever. But you get the point. My z-score and percentile rank relative to two other people I chose my sister and my mom. My z-score for the body mass index was 40, and so the z-score was 2, which is not healthy. And my sister was probably the healthiest out of all of us, which was 29 BMI score. Yeah, it was a calculator you guided us to. That's how we got that number. And then the z-score we just put on the plot, and then we just guesstimate. Or no, yeah, that's right. And we use the z-score table to get the exact z-score. Yeah. So like my sister was the healthiest out of all of us, and then my mom, she's just a little frail woman. Her BMI was 16, so her z-score was negative 1.9, which is just basically the polar opposite of mine, which, so we're not really the healthiest family, to say the least. Oh, and I forgot to say the topic title of this section: population samples and probability of distribution. Sorry about that. And then the next one is personal, state, and federal finances, which this was my favorite section, because to me quantitative literacy was described as basically, like years ago in high school, quantitative literacy was described to me as basically math, except math you can use in real life. So I was excited to actually get to the financial part of this. So in this slide, outliers that keep their distribution of American incomes of being normal. Basically, the rich here, this is the amount, the blue is the amount of wealth in the U.S., and the orange, I almost said purple, the orange is the amount of people that own said wealth. And of course, we can see that there's basically two different sets of outliers here, with the poorest wealth group, number one. Um, the poorest of the poor and the richest of the rich are clear outliers, and it just skews everything from being equal, from being normal, as to phrase it as the question did. But this is basically the same thing, but you can just really see, like, do you in a perfect world it'd be dead even, like just a flat line of just blue and orange. Of course, that's utopia, and that will never happen. Um, but yeah, we can see there's clear outliers. Like this small little sliver owns all this wealth, and then this huge amount of people owns just that little bit of wealth. Good old capitalism. And the struggling of starting a business, and relate the distribution of America income to struggling to start a business. So basically, I used this Elon Musk flamethrower run from the first report to show, well, to start a business, or in this case, sell flamethrowers, but to start a business, you have to make an initial investment and take a loss for a little bit, maybe a few months, maybe the first couple of years if need be. But you need to make an initial investment and then make loss um, to eventually gain profit. Um, so like we saw here, the initial profit was like, or the initial investment was about 10,000. And of course that kept decreasing because they had to make the flamethrowers. And if you make a business, you have to make whatever you're selling or whatever you do. And it wasn't until he sold over 200 flamethrowers, throwers, um, can't speak, over 200 of them, that he started making a profit. And you can see that there's a clear relation with how it's hard to start a business, was because if you look at these, there's too many people that own too little wealth, and generally the people that make mom and pop style businesses would probably be this age group here, or wealth group over here, 1 through 4. Um, I guess I guess you can quantify this as a upper class, lower class, middle class over here. But generally, this is the people making the businesses. But like, if you're in this wealth group, there's no way you could start a business, because you just have so little money to begin with. You can't invest it. You can't invest it in your business for it to thrive. And the age group, I keep saying age group, the wealth group number 4 would, and 3 would have the highest chance, but still, even theirs is pretty low. It's just a concern if you have enough money put aside, or you can afford to take that net loss for however long it would take to make profit on your business. And of course, my dad struggled through this. He used to own a furniture store on the airport, and that closed in I think 2008 or 2009 because of the financial crisis in '08. So it's just he couldn't sustain his business anymore. Of course, he already had that. That's a little different because we're talking about starting a business. He already had his business for a long time. It just profits went down. But I guess that's beside the point. Anyway, the inequality of wealth, it's basically the same thing as we talked about with the outliers here. The inequality of wealth is quite clear. This little percentage owns all that wealth. This huge percentage owns this little wealth. Pretty unequal. As I was saying, in a clear world of being normal, or a utopia, we'd want this to be dead even right here. But it's just never going to happen. The rich is going to stay rich, and that's just how it's going to work till we die, until they die, and just till the end of time, frankly. A little depressing if you think about it, so just don't think about it, I say. So where are our American tax dollars spent? Um, and I found this pie chart, which we made. I just totally forgot about it. Um, and basically just general percentages of where our money go, our tax dollars go. And I'm surprised only 16% of it goes to defense. I thought it was like a majority of it. But no, a majority of it goes to Medicare, Medicaid, CHIP. I don't know what that is. I forgot. And marketplace subsidies. I assume that's like food stamps. I think. I don't know. Social Security, safety net, and like this is just all the general percentages. Oh, I clicked. Um, it's just all the general percentages of what the government does with our tax dollars, and this is probably the saddest amount right here with education and medical research. Only a combined 4% of science and medical research in education. Only 4% is spent on that. It's a shame to say the least. Well, next slide. Depressing enough. Different ways we can pay taxes. This was a fun one. Um, there are different tax brackets, and you can file, not tax brackets. That's the wrong word. You can file different ways, depending if you're married or whatnot. So, and one or the other could be more beneficial to you if you do the math and you can see the end game of how your money would end up. So this one is, I believe it was the same, yeah, the same income of $50,000. Or yeah, that's right, we got a raise, and all this was equal. Okay, I guess this was a bad example, but I think on the next slide I have the filed as head of household, which was different disparity. But basically, you can pay a single filed file jointly, but in this case, it just didn't. It didn't make a difference of what you got at the end, because what the leftover amount. Oh no, it did. Yeah, the leftover amount single with this new pay, this raise in this job of the scenario we got was about 33,000, and then this one is about 40,000. Oh, geez. I guess that one's just a little squished, or the angle I'm sitting at just looks really, really different. But yeah, as you can see, different ways, more beneficial um, if you do the math or hire an accountant to see the end game of your finances so you can plan ahead for that. So in this case, filing jointly would have been more beneficial with the new pay and the old pay actually, which was not the case if you filed head of household, which is in the next slide. And how do tax brackets work, and how does the percent of taxes owned changes depending on your income, on the way you file? Basically, everything you said, tax brackets. I believe that was the how much money if you're filing. Oh, excuse me. If you were filing, if you're filing single and you make like $50,000, then okay, that's fine. And you're in that tax bracket to get a certain percentage out of it. But if you filed, I think, yeah, head of household, you had to make like I think 52,000 to get to that next. Or no, that's right. It was 50,000 for head of household to get in the tax bracket he was in to get taxed a certain percentage at the end of the year, the fiscal year at least. Um, and then when he got the raise, he was in this new tax bracket, which meant he got charged a higher percentage for the taxes. So what eventually happened, if he accepted this raise, it would not be worth it, because there is nearly a $10,000 difference if he took the new pay, and the new pay would be less. The new pay is around 30, and the old pay was around 40. So the raise honestly would only be good in the short term until you have to pay your taxes at the end of the year. So in this case, taking the raise would not be worth it. But At the same time, when you file jointly, that's under different types of tax brackets. So in this one, when it was 50,000 annual pay, and then I think it was 52,000, he was still in the same tax bracket, which the head of household wasn't. But this one, when he got the new pay, he was still in the same tax bracket, so nothing changed with his taxes. So it was worth it to take that new pay, that raise, which of course it was only $2,000 difference more, but still, I mean that's $2,000 that you didn't have to pay to the government. So yeah. Oh yeah, I've been annoying the center part. So obviously you can see when he went to that when head of household went to that new tax bracket, he paid way more tax, like nearly double, like very close to double the amount of taxes than he did in the previous tax bracket. So you want to keep an eye on that kind of stuff, or hire an accountant to do it for you, which it's usually probably good to have a good accountant. And the linear growth pattern of simple interest. Simple interest is the linear way of paying one back. A certain percentage every day or month, you generally every month when it comes from a bank, or interval, any other interval of time or year, whatever, what have you, could be any interval of time. It's just simple interest is the linear way of paying one back. It's it's a consistent interest rate. So let's just say like 2%. If it's a steady 2% of if we look at this graph right here, this was like it looks like $3,600. Okay, let's say I got I don't remember the interest rate, but let's just say 2%. Well, okay, I have to pay an extra 2% on that till I'm done paying it indefinitely. So it would be very linear because you're just adding 2% every time and the interest rate is not changing. So it is obviously very linear, as we can see on both of these graphs. But on the but then exponential pattern in the compound interest graphs, we can see is an exponential pattern. It's a curve instead of linear. Compound interest is basically certain percentage compounded daily, basically interest on interest. You don't want to pay a car, but pay a car. You don't want to buy a car if it has compound interest, which I don't think that's a thing. Um, but yeah, it's basically just interest on interest. So every day you don't pay them, that interest is going to get higher a certain percentage. So in this one we did quarterly compounded and continuously compounded, which I guess there's just a little just little differences in between those. I forgot what exactly, but there was a difference in between those. I'm assuming when you paid continuous compound and quarterly compound. I assume that depends on when you pay. So depending on when you pay, uh, of course, well, no, I won't say that because that's in the next slide with how fast you pay. Well, it would be cheaper. Um, but what's the right way to word this? Well, let's just say I buy a house or I buy this car, $20,000 car. Okay, cool. And then like in the event of paying it back, like basically paying the bank back of that money, or the car company of that money, um, they like with every payment, let's just say every month, let's say my simplicity's sake, let's just say my payment was $100 a month. Um, you'd finish paying that car at the end of your life. Actually, no, you wouldn't even own that car at the end of your life because that, well, whatever, $100 a month. Okay, you have to pay $100 a month. Okay, but that's with compound interest. Okay, $100 a month. Okay, but then the next month comes and it's probably going to be like $102, let's say. And I'm like, oh, okay, it's a little higher. That's weird. And the minimum pay, by the way. And then the next month comes and it's 100 and it's $106 a month. I'm like, oh wow, this is really getting up there. And then the next month comes and it's $112 a month, and it's not linear. It's just you. That's where that curve comes from. As you can see here, it's just big numbers, so I don't want to say it really much. That's why I gave my car example. It's just curved. It's not linear because of how you pay it, of what compound interest is. And I honestly I can't think of anything that has compound interest, but I guess that's uh, besides the point. I'm sure there's many things in it. I'm too young for that at the moment to see the world. Anyway, um, the difference. Oh yes, the house one. I love this. I love this one. I really did like this one. I just had a blast doing this whole one. The difference between what a house costs and what you pay in the end with interest, which I always do. The sooner you pay something off, the less you would end up spending on it. But it's nice to see like the actual numbers of this scenario. So like this one over here, if we just look at this one, I same down payment on this $150 house, same down payment of $80,000. The only difference is the loan type for this one is 15 years and this one is 30 years. So what that means is the interest rate for the 15 years is 3.5%. So eventually, with the interest, of course, you can eventually that with the monthly payment of 114, if you only did that minimum payment, it would be $208,000. 208,000, yeah, $208,000. So that house had about $60,000 in taxes, or taxes, interest, I mean, um, of interest. But then, exact same scenario, it's just that you paid it longer. I'm like, oh, well, the monthly payment is cheaper. So it must be like cheaper, or not cheaper. I doubt people think that, but like it's just easier on some people to do the 30 to pay it over 30 years. But with 30 years, the interest rate is 4.2%, which, oh, that's not much of a difference. And the monthly payment is 559. But the end payment at the end of that is astronomically higher. You're paying an extra 100,000, 130,000 actually, right? Yeah, basically $130,000 extra than you need to, based on the house price originally. And of course, I have the graph here to just show that in better terms. The first payment with 15 years on it is this much, and then it's just an extra 70,000 if you double the amount of time you pay for it. Yeah, and I'll talk about paying extra in the next slide. And then this is the exact same thing, just different down payment. The interest rates are the same, but with a different down payment, we still had a different end payment. So of course, the higher the down payment and the shorter amount of time you pay for it, the cheapest it would be. So of course, the cheapest option would to pay, like if you have this much money in the bank, would to buy that house right then and there, no interest rate. Which think I honestly don't know if you can do that. I don't think you can. I think you have to pay interest, but I'm sure I'm wrong on that aspect. But of course, like right here, it's a same down payment of $60,000. It's just different, the same time intervals. And the monthly payment for the 15, of course, is higher, but you pay less. And the monthly payment on this one is lower, but you pay astronomically higher. And then this is just these two graphs combined, just that clear difference. And it's just remarkably, oh, it's raining, and and it's just remarkable. I just found it so fascinating, like how much interest there can be. And of course, same thing applies to a car, I imagine. It just, this case was a house. But I just found this so fascinating because I've always wanted to do this, but just never had the willpower to do it. Um, And basically, I found a website that did it for me when it comes to the interest rates. It found that for me, but I just found it so interesting. But then, like options between buying your house of paying extra a month. So if we come back to here, we were paying with this $80,000 down. We were paying $714 every month, and the end payment was that. And I said if you paid that minimum monthly payment, but if you start paying extra, and I didn't do the math in this scenario, but I found this graph somewhere else. If you paid extra, you would end up paying less interest. Yes, interest. You'd end up paying, let's say, an extra $100 a month. You'd pay less interest every month, or at the end result of those 15 years. Or would it end? Yeah, no, yeah. I guess it would end sooner, like eventually, like because if you paid an extra $700 a month, an extra $100 a month, I mean, with the 700. So every 7 months, you would have paid an extra house payment. So that's basically a free month right there. So that's a month taken off the year. I imagine that's how it works. But anyway, eventually, if you pay extra, the less interest you would have to actually spend. As we can see here, I forgot what the intervals of money was, but let's just say this guy. Um, let's just say a house at the end result that it was this much, 177,000. But then if we paid an extra 30 or extra 50 every month, well then at the end we would have paid $7,000 less. But then if we paid double that extra, $100 a month, we would have paid 10, like nearly $15,000 less. So it's just stuff like that that you should consider. Well, not you, I guess you already own a house. That like people should consider, the general populace should consider when buying something that's of large quantity, like a house or a car. And I just found it fascinating, like to see putting different down payments and see like how that would change. Like I just thought it was a blast. Okay, and the different costs of living in your chosen state for Module 2 financial report. So this one, I have all my states here that I chose, and sorry about that. Basically, the only difference besides taxes was mainly just rent. But and keep in mind, I was very generous on the rent. Like I made it like super high. But this is yearly. This is yearly, not monthly. Um, so the rent was about 20,000 in Fort Smith, 24,000 in Seattle, and 18,000 Idaho, Idaho, Idaho. But basically, the main difference was the taxes. Um, and I would have been filing single, so I took that into consideration. I found the taxes the best I could. And in Arkansas, it would have been $20,000 plus my total expenses. So my total of like spending money would be $18,000, and of course I added that into like a spending fund and a savings fund. Um, but that's besides the point. And then Seattle, the tax was 17,000, which was $20,000 at the end. Where Arkansas was 18,000, this was nearly 21,000. And then with this one, taxes were 22,000. Yeah, 22,000, and the taxing, the total taxes and expenses were 22 or $21,000. So basically, the main difference between the states were mainly mainly just taxes and taxes, rent. Of course, that varies wherever you go, even if you cross the street. in like New York or something. But like the only thing I could think of is maybe food would be a little different. Like if you like live in the Midwest, like seafood or something like that. I don't know. And internet, like in one of those flyover states, would probably be a little more expensive. But besides that, I there's not much of a difference between these states that I chose. And why does making more in one city doesn't always mean more leftover income because the cost of living may be higher? Okay, and this one, why does making more in one city doesn't mean always mean that more leftover income because the cost of living may be higher? Well, it's basically the same situation as this. Let's say different states they have different tax brackets, as we were saying in a slide before. And it's basically back to this situation of filing head of household when he got this new raise. If he took it, he would have ended up getting less. It's basically than less than what his old pay was. And it's basically the same thing if you choose to live in a different city slash state. I'm just going to say state. If you choose to be in a different state, because every state has different tax brackets. Yeah. Every state has different tax brackets because there's the state tax and then there's the federal tax. Um, so yeah, every state would be a little different, and you have to keep that in mind when like moving to a city slash state. Um, but yeah, as you can see, well, I've already explained this in just the previous slide. I just in different contexts of moving to a different state rather than just taking this raise or not in this one state, which would cross the threshold of the tax bracket, which would result in you making less or getting less at the end of the year. Well, no, yeah, making less at the end of the year. But it all depends on that state's slash city's tax brackets. And of course, the cost of living may be higher. That's also a consideration too, of course. And then in this context, the cost of living may be higher. LA is a perfect example. LA, like apartment buildings are super expensive. So, like, let's say I have a job that makes $70,000 a year, and I'm living comfortably here, and then I move to LA and have the exact same job and exact same pay. I'm gonna make less. I'm just going to make less because the cost of living is significantly higher. Well, in California in general, but especially in like places like LA or something like that. And of course, the opposite is true. I keep looking over there because that's where my face cam is. The opposite is true with like if you choose to do a cheaper state, like a Midwest state or something, like where the cost of living would be significantly lower compared to LA, because LA is stupid high. Like I I don't understand how people literally like most people are scraping the bottom of the barrel just to live there for some reason. But that's another topic. Oh, that's the end. Oh wow, just noticed that light difference on my cam. So that's the end of my final presentation for quantitative literacy. And like I said, um, if I if I do those math connect math problems again, and I make 100 on them, and I make a 500 on this, I should get a point 89.5, which rounds to a 90. So if I get a 500 on this, and then I go ahead and get 100 on the connect math stuff, I should get a 90A in here. So let's hope that happens. Well, anyway, I hope to see you next weekend, or not weekend, next Wednesday, Miss Benzie. Uh, this was a fun class. Well, anyway, I guess you grade a lot of these, so might as well end it. I'm sure this is very very long. Anyway, have a good one. It was good having your class.